mysteries of dark matter and dark energy represent some of the most profound and challenging questions in modern astrophysics and cosmology. Together, they constitute about 95% of the total mass-energy content of the universe, yet their true nature remains elusive. This essay delves into the intricacies of dark matter and dark energy, exploring their discovery, properties, and the various theories proposed to explain them, along with the experimental and observational evidence gathered so far. Dark matter. Historical background. The concept of dark matter was first proposed by Fritz Zwicky in the 1930s when he observed the Coma cluster of galaxies. Zwicky noted that the visible mass of the galaxies was insufficient to account for the observed gravitational effects, such as the high velocity of galaxies within the cluster. He coined the term Dunkel Materia, dark matter, to describe this unseen mass that must be providing the necessary gravitational force. Evidence for dark matter. 1. Galaxy rotation curves. One of the most compelling pieces of evidence for dark matter comes from the study of galaxy rotation curves. According to Newtonian mechanics, the rotation speed of stars in a galaxy should decrease with distance from the galactic center. However, observations by Vera Rubin and Kent Ford in the 1970s showed that the rotation curves of galaxies remain flat at large radii, implying the presence of an unseen mass extending well beyond the visible matter. 2. Gravitational lensing. Einstein's theory of general relativity predicts that massive objects can bend light, an effect known as gravitational lensing. Observations of lensing effects, such as those seen in galaxy clusters, reveal more mass than what can be accounted for by visible matter alone. This discrepancy suggests the presence of dark matter. 3. Cosmic microwave background, CMB. The CMB, the afterglow of the Big Bang, provides a snapshot of the early universe. Precise measurements by satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite show fluctuations in the CMB that suggest a universe composed of about 26.8% dark matter. 4. Large-scale structure formation. The distribution and formation of large-scale structures, such as galaxies and galaxy clusters, are influenced by the presence of dark matter. Simulations of the universe's evolution indicate that dark matter acts as a gravitational scaffold around which visible matter coalesces. Properties of dark matter. Despite the overwhelming evidence for dark matter, its properties remain largely unknown. Some of the key characteristics hypothesized include non-luminous. Dark matter does not emit, absorb, or reflect electromagnetic radiation, making it invisible to current detection methods that rely on light. Massive dark matter must have mass to exert gravitational effects. Weakly interacting. Dark matter interacts very weakly, if at all, with ordinary matter and electromagnetic forces. This weak interaction makes it difficult to detect directly. Several candidates have been proposed to explain dark matter. First, we have WIMPs, or weakly interacting massive particles. WIMPs are a leading candidate. These hypothetical particles interact via the weak nuclear force and gravity, but not with electromagnetic force, making them difficult to detect. Experiments like the Large Hadron Collider, or LHC, and various direct detection experiments, such as Xenon 1T and LUX, are searching for WIMPs. Next, we have axions. Axions are another hypothetical particle, initially proposed to solve the strong CP problem in quantum chromodynamics. They are light and weakly interacting, making them a candidate for dark matter. Then there are sterile neutrinos. These are neutrinos that do not interact via the weak nuclear force. Unlike the known types of neutrinos, they could contribute to the dark matter density if they have a suitable mass. Lastly, we have machos, or massive astrophysical compact halo objects. MACHOs include objects like black holes, neutron stars, and brown dwarfs. While they contribute to the overall mass of galaxies, they do not account for the majority of dark matter. Several methods are employed to detect dark matter. Direct detection experiments aim to detect dark matter particles interacting with ordinary matter. Techniques typically involve ultra-sensitive detectors placed deep underground to shield them from cosmic rays and other background radiation. Indirect detection involves searching for the products of dark matter annihilations or decays, such as gamma rays, neutrinos, or positrons. Instruments like the Fermi Gamma Ray Space Telescope are used for such observations. Finally, collider searches involve high-energy collisions in particle accelerators like the LHC, which may produce dark matter particles. These would be inferred from missing energy and momentum in the collision products. Dark energy was discovered through observations of distant Type Ia supernovae in the late 1990s by two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team. They found that the universe's expansion is accelerating, contrary to the expectation that it should be slowing down due to gravitational attraction. This acceleration implies the presence of a repulsive force, now termed dark energy. The nature of dark energy remains even more mysterious than that of dark matter. Some of its proposed characteristics include: dark energy is thought to be evenly distributed throughout space, unlike matter, which clumps into galaxies and clusters. This is known as being homogeneous and isotropic. Dark energy has a repulsive effect due to its negative pressure, leading to the accelerated expansion of the universe. The relationship between dark energy's pressure and density is described by its equation of state parameter, defined as W(E)P(R). Current observations suggest W(1), which is consistent with a cosmological constant. Several theories have been proposed to explain dark energy. First, we have the cosmological constant, proposed by Einstein. It represents a constant energy density filling space homogeneously. It is mathematically simple and fits current observations well, but lacks a compelling theoretical explanation for its value, which is often referred to as the fine-tuning problem. Next, there's quintessence. This theory posits a dynamic field whose energy density can change over time. Unlike the cosmological constant, quintessence fields evolve and may provide a more natural explanation for the observed acceleration. Some theories suggest modifying general relativity to account for dark energy effects. Examples include FR, gravity, and brane world models. These theories propose that the accelerated expansion is due to deviations from Einstein's equations on large scales. Lastly, we have holographic dark energy. This theory is based on the holographic principle, which suggests that all information in a volume of space can be described by data on its boundary. Holographic dark energy models attempt to link the energy density of dark energy to the universe's size and horizon. Observations of Type Ia supernovae. As standard candles help measure the expansion rate of the universe at different times. The accelerating expansion inferred from these observations supports the existence of dark energy. Detailed measurements of the cosmic microwave background, particularly from the Planck satellite, provide constraints on the universe's overall energy content, including dark energy. The CMB's temperature fluctuations offer indirect evidence of dark energy's influence on the universe's expansion history. Baryon acoustic oscillations are regular, periodic fluctuations in the density of the visible baryonic matter of the universe. These fluctuations serve as a standard ruler for measuring cosmic distances and expansion. Observations of BAO in galaxy surveys, such as the Sloan Digital Sky Survey, support the existence of dark energy. The distribution and growth of large-scale structures in the universe, such as galaxy clusters, are influenced by dark energy. Surveys that map these structures help constrain dark energy's properties. Despite significant progress, many challenges remain in understanding dark matter and dark energy. Identifying the exact particles or objects that constitute dark matter remains elusive. No direct detections have been confirmed, and theoretical models continue to be tested and refined. The fundamental nature of dark energy is unknown. Is it a cosmological constant, a dynamic field, or something else entirely? Resolving this question requires new theoretical insights and more precise observations. Both dark matter and dark energy pose significant challenges to our understanding of fundamental physics. They require new physics beyond the standard model and general relativity, prompting the development of new theories and models. To help visualize these concepts, consider the following illustrations. First, a graph showing the rotation speed of stars in a galaxy as a function of distance from the center, highlighting the discrepancy between observed speeds and those predicted by visible matter alone. Next, an image depicting the bending of light from a distant galaxy by a massive galaxy cluster, illustrating how dark matter's gravitational effects are inferred from lensing patterns. Then, a map of the cosmic microwave background's temperature fluctuations, with annotations indicating how these fluctuations provide evidence for dark matter and dark energy. Additionally, a graph showing the redshift of Type Ia supernovae versus their distance, illustrating the accelerated expansion of the universe and the need for dark energy. Finally, a visualization of the cosmic web, depicting how galaxies and galaxy clusters form along filaments and nodes, influenced by dark matter's gravitational pull. To deepen our understanding of dark matter and dark energy, several upcoming and proposed experiments and observatories are expected to play critical roles. Direct detection experiments. Future detectors will push the sensitivity limits further, aiming to detect WIMPs or other dark matter candidates. Experiments like Lux-Zeppelin, or LZ, and the Super Cryogenic Dark Matter Search, known as Super CDMS, are among the leading initiatives. Indirect detection observatories like the Cherenkov Telescope Array, or CTA, and experiments such as AMS-02, the Alpha Magnetic Spectrometer on the International Space Station, will continue searching for signals of dark matter annihilation or decay. Collider experiments. The high-luminosity LHC and future colliders like the proposed International Linear Collider, or ILC, and the Future Circular Collider, or FCC, will explore high-energy collisions, potentially revealing new particles that could be dark matter candidates. Astrophysical surveys. Projects like the Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, will map billions of galaxies, helping to elucidate dark matter's role in structure formation and evolution. Supernova surveys. The Legacy Survey of Space and Time, or LSST, will discover and monitor thousands of Type Ia supernovae, providing more precise measurements of the universe's expansion rate. Cosmic microwave background. The Simons Observatory and future CMB Stage 4 experiments will provide even more detailed measurements of the CMB, offering tighter constraints on dark energy's properties. Galaxy redshift surveys. The Dark Energy Spectroscopic Instrument, or DESI, and the Euclid space mission will map the large-scale structure of the universe with unprecedented accuracy, improving our understanding of dark energy through baryon acoustic oscillations and redshift space distortions. Gravitational wave observatories. Observatories like LIGO, Virgo, and the future LISA The Laser Interferometer Space Antenna will provide new insights into the nature of dark energy by studying the expansion of the universe using gravitational wave sources as standard sirens. Advances in understanding dark matter and dark energy are not confined to astrophysics and cosmology alone. Interdisciplinary approaches incorporating particle physics, theoretical physics, and advanced computational methods are crucial. Particle physics. Theoretical models from particle physics, such as supersymmetry and extra dimensions, offer potential explanations for dark matter. Cross-disciplinary research bridges gaps between high-energy physics and cosmology. Theoretical physics. Concepts from quantum field theory, string theory, and beyond standard model physics propose mechanisms for dark energy, such as modifications to general relativity or new scalar fields. Computational cosmology. Simulations of cosmic structure formation, dark matter interactions, and the universe's expansion rely on high-performance computing, providing theoretical predictions that can be tested against observations. The study of dark matter and dark energy also raises profound philosophical questions about the nature of the universe and our place within it. These include the limits of observability. Much of the universe is composed of dark matter and dark energy, which we cannot observe directly. This challenges our understanding of what constitutes reality and the limits of empirical science. The nature of reality. Theories like the multiverse hypothesis, where different regions of space may have different physical laws, challenge traditional notions of a single, unified reality. The role of human cognition. Understanding the universe requires not only sophisticated technology, but also the cognitive ability to interpret complex data and theoretical models. This interplay between human perception and scientific discovery is a key aspect of cosmology. In conclusion, the mysteries of dark matter and dark energy represent some of the most significant and challenging areas of modern science. Dark matter, accounting for approximately 26.8% of the universe's mass energy content, is inferred from its gravitational effects, but remains undetected directly. Its nature could range from WIMPs to actions, or even modifications, to our understanding of gravity. Dark energy, making up about 68.3% of the universe, is responsible for the accelerated expansion of the universe. It could be a cosmological constant, a dynamic field, or a sign of new physics. Ongoing and future experiments, interdisciplinary research, and theoretical advances will continue to push the boundaries of our knowledge, potentially leading to groundbreaking discoveries. Understanding dark matter and dark energy not only deepens our comprehension of the cosmos, but also challenges and expands our fundamental concepts of physics and reality.